In 8b, we cover doubling time and half-life, or exponential doubling growth and exponential half-life decay. So we have, after a time t, an exponentially growing quantity with a doubling time of t dub or t double or td increases in size by a factor of 2 to the t over t dub. So that's setting us up for the formula that we essentially used in the previous the last example of the last video in 8a. But it gives us this formula here. Our new value could be a population of people, bacteria, animals, virus, is equal to the initial value or the initial population, or even it could be a monetary value as well, times 2 to the t over t double or t dub, a doubling time. So another way to see this formula is P, population, that's what we might think about it, is equal to P naught, P sub 0, or the initial population, times 2 to the T over our doubling time, TD. So I might write it that way in places. So an appropriate example to look at is one involving COVID-19 infections. So on January 21st, 2020, actually, sort of the first official recording of the number of cases of COVID-19 infections. So on that day, there were approximately 280 cases recorded worldwide. By the middle of April 2020, or early April 2020, the cases had grown to about 1.8 million worldwide. I was able to calculate that yields a doubling time for the population of infected individuals of about 6.5 days. So in other words, T double, based on the information above, is equal to 6.5 days. This is all done for us in this problem. We don't have to worry about where I came up with those numbers. We're just going to use this fact to build a doubling time model for this spread of infection. So part A says construct the doubling time function, which calculates the number of cases based on the number of days passed since January 21st. January 21st is time t equals 0. It's 0 days past January 21st. So moving forward into the future, we'll count by days, and we know our doubling time, TD, is 6.5 days. We know that on January 21st, we had 280 cases. That tells us P naught, our initial value. That's the initial population or the initial count that we had in place. So using our formula above, P, or our new value, is 280, P naught, times 2 to the T over our doubling time, and that's 6.5. So just to be careful, I'll put that in parentheses just to emphasize this. So this is it for this part of the question. This is that model. This tells us, it's an estimate or a predictor for if we're t days into the future, this value right here, t days into the future, it tells us how many people should be infected based on this model. Now it'll have varying degrees of accuracy, as we'll see when we get to the bottom of this, but we can interpret that more or less to real-world scenarios. So use this function, this is part B, to calculate the number of cases 80 days into the pandemic. So 80 days later, so t is equal to 80 days after January 21st. So what we're looking for is the population, or the count of infected people when t is equal to 80. So the population based on 80 days is 280 times 2, and that 80 is plugged in for t over 6.5. When we plug this into a calculator, I'll stress be very careful with that. Make sure that that's an exponential expression and it has parentheses around it. That whole fraction right here needs to go into the calculator. Okay, what comes out of that is approximately 1,419,524 cases. This is rounding to the nearest whole case or whole person. So that's the projection in 80 days into the future, which is about correct if you look at the actual data. 80 days after January 21st is something like April 10th or so, somewhere in that zone, and that more or less meets the numbers Things start to get a little bit more out of hand, though, as we predict further into the future. So part C says, look, 180 days into the pandemic. And this would be a situation where, if growth for this infection rate was just completely unchecked, no mitigation measures were put in place, no social distancing, there was no immunity to it, it just courses through every member of the entire world population. But let's see what the result of 180 days later would be. So T is 180, once again, and we have our formula, same value, same formula we put together up top. I'll just repeat it here just to see it. P of T, so the population based on, or the population of infected based on time T, however many days after January 21st, is 280 times 2 to the T over 6.5. Writing the full formula down just as a reminder, we're using this each time. So P of 180, this means plug in 180 for T, using this function for us, 280 times 2 to the 180 divided by 6.5, and this actually approximately comes out to a rather large number. It's in the tens of billions. It's 6.07. I'm just going to round it to 6.07 times 10 to the 10th, which, just to make one slight adjustment, and maybe I'll add one more decimal here, 3, is 60.73 times 10 to the 9th. And I went to 10 to the 9th because that's billions. So that's 60.73 billion people at day 180. So sure, that's accurately calculated from this model, but we might note that something does not quite make sense, and that's always important with one of these mathematical models that we'll use, is it doesn't always reflect reality. In this situation, the extra bit here at the bottom says, compare these values to the fact that the Earth has about 7.8 billion people living on it. Well, in the case of part B, we had 1.4 million cases. That's perfectly reasonable. Well, maybe not acceptable, but that's at least mathematically possible. And in part C, unchecked, the number of infected grows to 60.73 billion, but we only have 7.8 billion. So we sort of blew past our realm of possibility in this situation. But 60.73 billion is too large. Since there are only 7.8 billion. But the conclusion we could make from this in terms of reality would be that at some point, if we're going to reach 60.73 billion, we would have reached 7.8 billion along the way. And when we would have done that, then that means that everybody would have been infected. There would have been nobody else to be infected, and the disease would have essentially completely won, I guess, in some sense. So that's our first doubling time model. Let's look at half-life. So half-life is very similar. It's just instead of growth, we have decay. So after a time t, an exponentially decaying quantity with a half-life of t half, just like t double, decreases in size by a factor of 1/2 to the time t over the doubling time capital T, or the half time capital T. Okay, this should actually be TH. Okay, the new value of the decaying quantity can be calculated with this formula, which looks quite a bit like the previous formula we had. I'll probably use P equals P naught times 1/2, or 0.5 even, to the T over T half, or half-life time. Okay, so this example is price of computer hard drive memory per megabyte. So it's kind of a common scenario to go for the value of something in terms of exponential decay or possibly even growth. So it's pretty well known that computer equipment becomes cheaper and cheaper, and sort of a exponential growth rate, or decay rate, an exponential decay rate. So if we look in this example, in the year 1980, the price of computer hard drive memory was $6,480 per megabyte. So $6,480 for 1 megabyte of storage on a hard drive. So the US dollar per megabyte cost of computer hard drive memory over time has an estimated half-life of 1.7 years. Okay, this was approximated from data found on the internet. It's reasonably accurate. So let's see where we're at now. This is actually, it's our half-life. It's a time, so we can write it down as T half, or TH. Okay, construct the formula which calculates the US dollars per megabyte cost T years after 1980. So in other words, we want to be able to predict what the cost per megabyte of cost of hard drive memory in US dollars per megabyte will be at any point in the future. And we'll be able to do this with varying degrees of accuracy. So what do we know here? P is equal to P naught times 1/2 to the T over our half-life time. Well, P naught, the only original amount that we know is this rate for the cost, $6,480 per megabyte. So we'll use that. So our future cost per megabyte, P of T, based on time T, is equal to this $6,480 per megabyte times 1/2 to the T over T half is 1.7. And we'll note that this is in years. Okay. Not days or months, but that's always going to be specific to whatever problem we're working with. So this is in terms of years. And this is exactly what we're being asked to find. We have a completely determined formula for P, and it's only based on T, time. In this case, time is years after 1980. So they ask us to calculate the cost per megabyte in the year 2000. So the first thing we need to know is this. T is equal to however many years have gone by since 1980. We use this value, 6,480, that was from 1980. So any number of years past 1980 is the way that we'll come up with T, our number of years. So that's 2000 minus 1980 is 20 years. So that's our T value. The price for T equals 20 is given by 6,480. Plugging this into our formula that we built in the previous part, 1/2 to the 20 over 1.7. And this comes out approximately to something like $1.86 per megabyte. So we'll leave off the dollar sign and just put 186 US dollars per megabyte. So in 20 years, the price went from $6,480 per megabyte to $1.86 per megabyte. It's becoming a little bit more familiar to us. I don't think that any one of us would have paid $6,480 for a single megabyte of data storage at any point in our lives. Anyway, part C, calculate the cost per megabyte in the year 2020. So that's even further. Again, we need to find the number of years elapsed since 1980, since that's the value that we used as the start of our model. All right, so time since 1980 is 2020 minus 1980, and we get 40 years. And then the price, 40 years later, is equal to 6,480 times 1/2. 40 is T, 40 over 1.7, and this comes out to, this is very low actually, 0.000535, picking an arbitrary number of decimal places, US dollars per megabyte. So I can box that up and maybe think about it even more specifically. So it's $0.0005 doesn't quite make sense. Let's convert it to cents. 0.0535 cents per megabyte. And while that's accurate, it still is a little deceiving. That's not 5 cents. That's 0.05 cents. That's less than 1 cent per megabyte, just to keep track of the units. So it's wildly smaller, wildly cheaper than even in the year 2000. It's not even a penny for a megabyte. So 2 different ways of interpreting that answer. Okay, so let's see doubling times. So to determine a doubling time, if we happen to know the rate at which something grows. So this is particularly useful if we're looking at a bank account or a stock value that's growing at some reliable rate. For instance, this example right here, stock's value is growing at a rate of 2% per month. We're asked to find the exact doubling time for that stock's value. So how long will it take for that stock to double in value? The way to do that is right here. We look at this example. We have log 10 of 2 divided by log 10 of 1 plus r. And r, we'll notice, is the fractional growth rate. In other words, it's our percentage of growth. So this formula tells us how to find this doubling time. One thing we should note about this log 10 is it's just the logarithm button on any scientific calculator. So you might write it as this. It's common log. Common log is the log without any number on the bottom, but it's understood to be log base 10. And even if you used natural log of 2, the ln button, either one of these will work. Whichever one you can find reliably is the one to use. Don't mix and match. Don't use log and ln, one or the other. Use them both as you see them here, one exclusively or the other one exclusively. Okay. So anyway, let's have a look down here. To calculate the doubling time for this stock's growth, T-dub, we have log of 2, as the formula tells us, divided by log of 1 plus r in this case is 2%. And that's a monthly rate. Interestingly enough, we're told it's a monthly rate. We might have assumed it was APR. We write it down as 0.02. And when we plug this into a calculator, be careful to use parentheses around the logarithm's arguments here and here. But what we get out of this is approximately 35 months, or we get 35.003, rounding that. And this is about 35 months. We can round to this. Okay, we might be curious, how did we know that this was in months? Well, this was our clue, per month. If we're given a unit of time for this rate, then that's going to determine the unit of time for our doubling time. 35 months, by the way, to be a little bit more, conventional about how we express this, that's 24 months, which is 2 years, the largest factor of 12 that goes into 35, plus 11 months to get to 35. So that's 2 years and 11 months, just in case we needed to convert that to this form. 2 years and 11 months. If we weren't asked to convert it that way, then this one's just fine. Either of these works. So that's our doubling time. In 35 months, the value of that stock will have doubled. So 2 years and 11 months, that stock will double. Okay, the half-life formula. Very similar. Notice there's a minus sign. Another thing to keep track of is our rate should be less than 0. So if we have an exponential decay rate, we want to make sure that we make it negative. Okay? So let's see that in the example below. So if the value of a particular nation's currency is decreasing in value by 10% per year, determine the time it takes the currency to lose half of its value. In other words, what's its half-life time? So let's see, T half is equal to negative log 2. I'm using that minus sign that's in the formula. Log 2 is up top. Again, that's common log. We don't have to put the base 10. We can use any logarithm we like. There's log and ln in calculators, so either of those is fine. And then we have log of 1, and then plus, what is r? It's a decay rate, so it's negative 10%, which is, as a decimal, negative 0.1. So negative 0.1 added to 1, or 1 minus 0.1, or working through this. It's 1 minus 0.1. This is actually log of 0.9. So when we plug this into a calculator, we'll get approximately, we'll leave the negative sign out front. What we get out of our calculator is the following: negative 6.58 years, rounded to 2 decimal places, years. I have 2 minus signs here and here, so they cancel to be a positive. There's 6.58 years. Again, how do we know it was years? Well, it's because 10% per year was given at the beginning of the problem. It determined our unit of time from the start. So that's it. That's calculating half-time and doubling times for anything, really, anything that's exponentially growing or exponentially decaying. So practice problems from this section, and good luck.